Alright, time for another DraftPhysics.com video presentation. So, physicist Michael has made another lever preview video. So, pretty much going over some of the same statements he's made about how the lever works in terms of his predictions and what math he's applying to make those predictions. And I'd almost argue that, to me, the math is so simple that you really don't need math. Frankly, you can just draw the math. So anyway, I will do some of that. And then we'll play some of the video. And I've only gotten halfway, and we're to his predictions, which is the important part. And so we'll talk about that. Ooh, yeah. Okay. Alright, so simple enough experiment, but as I stated, first you have to establish some sort of rules. Now, what I'm arguing is this: basically, a lever fixes what a Newton's cradle can't do. So a Newton's cradle can't do uneven masses. If I have the same mass and I crash into the same mass, I can take all of the energy here and put it into the other object. So, this can move in, stop, and this will leave with the same velocity. I'll conserve the momentum. But I can't do it with uneven masses because the acceleration doesn't match the deceleration of the objects. So they can't do the conversion. There's not enough time, I would argue, but it doesn't matter why it can't happen. It just doesn't happen. And my simple argument is that the lever provides an opportunity to fix that, because it basically does do the acceleration rate, deceleration rate. So levers, this part of the lever will move this much in the same time that this part will move twice as much. Not that difficult to understand. And with that understanding, you can understand that you can now do the conversions, that you can have something decelerate slowly, something heavy, decelerating slowly, and it could lift something accelerating quickly that's lighter. So you can put a half mass, twice the distance, and you can basically do what the Newton's cradle can't do, which is convert the slow deceleration into a fast acceleration. And it's just that simple. There's nothing else taking place. It's really just doing a momentum conversion. A lever converts momentums. It takes a big M and a small v and converts it into a big V and a small m. So the cradle can't do that, but the lever can. So any mv I put over here, I can change to any vm over there. And it's just that simple. There's nothing else going on. Now, for this experiment, the thing that's necessary, is first to establish what we're losing to the lever. So physicist Michael argues that the lever isn't doing a linear velocity conversion, and I would argue yes it is. Number one, because this rotation is going to be very small because it's a very long lever, and the objects aren't stuck to the lever, so they don't have to rotate. Alright, they can just go straight in and straight out. Alright, there's no necessity that they take any curved path. So you don't have to worry about the fact that it's not perfectly linear. It's going to be close enough to linear. Especially considering he's going to be using a cart with tracks. Okay, and the tracks are clearly going to require the object to move in one dimension, not two. So it's, to me, a moot point as an argument that this is something about rotational momentum, angular momentum versus just linear. Linear works just fine. Now the angular equation is pretty much the same as the linear equation, so it doesn't matter much. Now the other conversation is about the friction, or the force, that fulcrum produces. Now, I would also argue that that's a moot point because it is essentially a bearing, and the whole point of bearings is to minimize any friction, any capacity for energy to be absorbed. So it's a solid foundation that doesn't move, so it won't absorb momentum. And so all you have then is the mass of the lever. So the mass of the lever is going to matter, because the fact is whatever I push into the lever with, it's going to have to move the mass of the lever, okay, give it a velocity. So that will consume some of the energy of whatever object you put in, and you have to compensate that for that. So as I suggested, the first experiment should be plow the cart, I'd say as heavy as possible, to minimize the weight of the lever by comparison to the weight of the objects you're manipulating the lever with, and test to see how much friction, how much the weight of the lever absorbs, so how much energy is consumed in turning the lever. Now if it's a good bearing, this should be not too much, okay? It should be minimal, and that would be the hope, is that you have something like 85% of your energy conserved. That is, you don't lose more than 85% of your velocity by just turning the lever. So plow the cart into the lever, move the lever through a quarter of a rotation, and see how much velocity you have left, and that'll tell you how much you lost just moving the lever. Now once you know what that loss is, which is the L equation in his equation, some kind of L thing he calls it, then you can know that, well, that changes the momentum of the object. So the momentum is reduced by the amount of energy the lever itself absorbs. So again, if the lever is really light compared to the objects, it doesn't make any difference. So a teeter-totter, for example, you put a 100 or 150 pound person on a lever, it doesn't going to absorb much because the board itself doesn't weigh that much. 5 pounds, 10 pounds, could be as little as. And so if we can't get those kind of percentage numbers, 1 to 10, the fact is it's going to be a real issue moving the lever. But anyway, so once you know that number, how much you've lost in terms of the momentum by just moving the lever, then you can know, well, if you put the same object on the other side, which your expectation is that you should get that 85% number. Okay, so if you got 85% of the momentum is conserved, then when you put a weight on here, you'll know your highest expectation is 85%. Now, when you put the other object over here, you have to know you're starting with 85% of the momentum, the initial momentum. That means you have to slightly adjust the point at which you place the other object, giving it a slight advantage, that is, making it a little bit lighter, if you're going to restore the original velocity. So if you want to get the original velocity, you're going to have to move the object in a little bit to compensate for the momentum you lost. And it should then be equal. So the amount you've lost to the moving of the lever, then you're just going to convert what's left, the 85%, making that tiny adjustment, that 15% adjustment in position, to compensate for the 15% you lost moving the lever. And that should produce an output that would be everything except what you lost. Okay. So, but you should be able to see that actually happen. The closer you put the heavier mass, there should be a point where you get a maximum velocity. Too far out, you won't get it because it'll bounce. Too far in, you won't get it because it's too light. Alright. So that's the starting point, is that your numbers are going to be a little bit off depending on how much energy your lever absorbs. So that's the first thing to find out, is to drop the 2 mass and have a 2 mass at the appropriate location and see if you can get these two velocities to equal each other. Conserve the energy that went in and produce it out, minus your losses to moving the physical mass of the lever. Alright, so that would be a first step. Then when you do the actual experiment, I would say that the prediction is going to hold, that you can in fact drop the 2 mass at one distance, push the 2 mass, okay, at a velocity, and that you have every expectation that the half mass, the 1 mass, will leave, okay, with twice the velocity or a little bit less. Like I said, you might have to put it a little bit closer to get the deceleration to match the acceleration. And I think that's quite possible, that you could move it in a little bit and get a little bit more velocity to the match of the velocity to the actual deceleration to the actual acceleration. It'll be possible, which will be the 85%, depending on how much friction there is, and that it will be conserved. You'll conserve the momentum, the mv here will be conserved here, minus the amount you sacrifice to the weight of the lever. So that's not very complicated. So the idea would be is that, yes, okay, full mass in here consumes all of the momentum is used, crashing into here, nothing's left over, and this will leave with almost twice the velocity minus the 15% you might have lost to moving the lever again. So, but you'll conserve the momentum in both the weight of moving the weight of the lever plus this object will add up to what went in. All right, so with that context, so first you really do have to know how much the lever's taxing the experiment, and then you can do the experiment. All right, so I don't know if I even need to play all this because it really doesn't say anything, but I guess we might as well do some of it just to be I don't think it's being fair, but I think it's just being redundant, but we'll do it. And so we're at 16.
In terms of its kinematics, how do we describe that motion? In terms of Newton's laws, or in terms of conservation of energy, or conservation of momentum, or conservation of angular momentum. So in this one, I want to apply this to the upcoming lever experiment and figure out, well, which tools are we going to be able to use, and can we use those tools to build a model of this lever system that can...
All right, so I'm arguing there is no model because you have no model for kinetic energy at all. So momentum is a model in the sense that momentum is by definition, okay, a quantity of motion. It's something the object possesses by moving, and the idea is you have to conserve the movement. Now, their theory is that there's plus and minus momentum, that somehow you can move something this way and that way, and as long as they're opposite directions, that somehow you didn't use any energy. That is, you could hit two things this way and move them this way, and somehow because they're in opposite directions, I didn't use any energy to move them. That kind of thing, which obviously, in my opinion, doesn't make any sense at all. There is no negative motion. There's only positive motions, and any motion has to be accounted for in that it had to use something else's motion. Something can't acquire motion unless something that has motion has interacted with it, either the raw force itself or an object that possesses the force. One of those two things has to interact with it. As Newton said, twice the velocity, twice the force. 3 times the velocity, 3 times the force. The force is momentum. All right, continuing.
Make specific quantifiable predictions of what the outcome of the experiment is going to be, and then we'll be able to say the experiment will allow us to put those predictions to the test. So let's just quickly talk about what this lever experiment is going to be.
So again, the predictions have to be in the context where you agree on what exactly is going to be absorbing energy in the system. So just as he called them external forces, he calls the fulcrum an external force. It's not an external force, it's an internal force. And all I can do is take energy. It's not going to give any energy. So it's just a matter of questioning how much energy is going to be absorbed in causing the lever itself to move.
So we're going to have a horizontal lever, so something that can kind of rotate in a horizontal plane. And we're going to say mass M1 hits this directly, so it's a right angle hit to the lever at one end at a distance of R1 away from the fixed fulcrum point.
And so I would argue that if it does hit with M2 at the right position, that is, if the acceleration is going to match the deceleration, and you've got those matched correctly, 2 to 1, then the hitting will not be a bounce at all. You won't need Velcro, because it will be like the Newton's cradle. The one object will essentially put all of its energy into the other object in a very efficient manner, and there won't be any bouncing issues.
At an initial speed of v0. When this hits, the lever is going to rotate and launch mass 2, which is a distance r2 from the fulcrum point. And we're going to be looking at how fast is m2 being launched, how fast is m1 moving after, what's going to be happening with the rotation rate of the bar afterwards. And again, we want to try to predict how is this system going to act if I use different masses, or if I...
So the system also could be converted into a system that was done by Stephen Brough, where instead of using two opposing moving objects, you use the same force, and you just apply a raw force from a spring against the object. And that also is probably an experiment worth seeing somebody redo well. And the simple argument is you're using the same force. You move the lever, compress the spring with the same force, and then you just do the simple experiment of launching a 2 or launching a 1. And in the case of the Brozo, it was essentially a 2 to 1. Okay, this went 11, this went actually 19, and this, well, it was closer to 20 actually. So 20 to 11, I would say, were even better numbers. But anyway, very close to a 2 to 1 relationship. Applying the same force, and by applying the same force, you also have the same losses in the system moving the lever, so it doesn't have an effect on the experiment, which is also a nice benefit, is that whatever force has got to be used to move the lever, it's already built into the compression of the spring, so it's equal for both experiments. So in a sense, it's a better experiment to do. But anyway, so just pointing out that that experiment has been done. Now, the fact that we don't have this experiment, it's something, it's a simple question. This is a 1,000-year-old device, a lever. And the fact is that we don't have any experimental evidence demonstrating what happens when you apply a force to this side of the lever and actually launch objects with a lever. Now, you have catapults and trebuchets, and all of those, I would argue, do demonstrate the 2 to 1 relationship. You just put something lighter further out, and you get more and more velocity. And that it does conserve the momentum of the, in the case of the trebuchet, the object dropping through gravity. But we really don't have any explicit, clinical, scientific experiments demonstrating exactly how well levers convert momentums, how well they convert the big M and the small v into the big V and the small m. How well do levers do these conversions? And the fact that they don't have any of that scientific evidence is, in thousands of years, frankly, that it's not been documented in any way that I know of to find any documentation, is glaringly silly for it to be called a science when they haven't done this simple investigation of a very simple and rudimentary functional tool that has been used in, literally millions of ways to convert momentums. It's just an amazing statement about how lame and weak the science has been.
Place those masses at different locations along the bar. So let's see what tools are going to be most useful to allow us to analyze the system to, again, be able to make predictions that we can then put to the test by actually doing the experiment. So let's look at the system first in terms of linear momentum and identify whether we can use conservation of linear momentum to analyze this particular system. The alternative model of this lever experiment that has been proposed by DraftScience is that if you place the...
So what is bizarre is he has a little arrow here for M1, and M1's the one we're actually applying the force with. And he's claiming that somehow M1 can't use all of its energy, that it'll always contain an after. So it's V1 before and then V1 after. And the whole idea is to have no V1 left over. The whole idea is to convert the energy completely.
the objects in such a way that the torques would balance if we hung these masses up and tried to balance this on that fulcrum point. So say M2 is half the mass of M1, but at double the distance. Then in his model, we can use his version of conservation of momentum and say that all of M1's original momentum will go into M2. So if M2 is half the mass, it should be launched with double the speed that M1 originally had before hitting the lever. Or if M2 was 1/3 the mass, but at 3 times the distance, it should be launched with 3 times the velocity. Now, this would violate the textbook physics description of conservation of energy, but...
Okay, so again, it would violate the kinetic energy theory, okay, because yes, it would be free kinetic energy. So let's just be clear, but it doesn't violate any momentum arguments. It certainly doesn't violate anything Newton believed in. So, you've got to be a little careful about what you're claiming it's violating in terms of what part of the textbook it's violating. Okay, it's not violating the part NASA uses.
That's a part of his model, and we're going to be, when we actually do the experiment, we're going to be comparing against this. Which model is more accurate? The standard textbook, physics textbook description of physics, or...
It's not in the standard textbook model of physics, so you won't find this, experiment done in your standard textbook.
His model. So what does the kind of standard textbook physics description of this system say about whether we can use linear momentum? Well, the total linear momentum...
So that's this textbook doesn't say a damn thing. So let's just be clear about how levers function and whether objects that interact with a lever are being obliged to rotate, because they clearly aren't being obliged to rotate. They can slide a little bit. The wood can slide over the object. The object can maintain its linear condition, and it doesn't have to do any rotating at all. So it's not true to say there's any standard textbook that says levers don't apply. You can't apply linear equations to a lever, when I think of course you can, especially the longer the lever is, the less any rotation has any relevancy.
Is only going to be conserved in the case where there are no external forces acting on the system. If I have two objects run into each other,
So there's no external forces in this system. You could do this system in space as long as you nailed this fulcrum to, say, the side of the space shuttle or something. It's not going to be an issue. There's no external force. Bearings don't create external forces.
There are only internal forces between things that we say make up that system. That's when we're going to get this conservation of linear momentum. But in this case, when M1 hits that lever, there's going to be an external force at this fulcrum. Otherwise, when mass M1 hits the lever, the entire thing is just going to fall.
So, of course, it's not going to do any of that stuff because there is a bearing, and the bearing compensates, basically creating... That's why you have two sides to the lever. It's basically one side compensates for the other side, and the bearing pushes the energy from one side to the other side. It does the converting. So there's very little loss to the bearing itself. You still do have to move the mass of the lever, so that's still going to be an issue.
Just get pushed away. So since there's going to be an external force at this fulcrum point during the hit, linear momentum will not be conserved. This is not the right tool to use.
So again, it's just nonsense, I would argue. There's absolutely no reason to believe linear momentum won't be conserved, that it is every time that levers have ever been used. You're conserving the linear momentum, substantially. So it's just not a rational or reasonable argument. The rotation has very little to do with anything anybody does with a lever. Levers aren't operated in, 360-degree arcs. And even if I were to operate one as a gear and move it through a rotational degrees, it's still linear. It's still perfectly 2-to-1 in terms of distances and velocities. So I get the same impact if I flip a lever like this. If I have a hinge here and I just flip something in 90 degrees, I haven't changed this 2-to-1 relationship at all. I haven't changed the lever at all. And what I'm going to get as a final is that this object will travel twice the distance in the same time that this object will travel 1 unit of distance. So nothing changes. I think this is just a dodge. I mean, this is not true that you change anything by pretending that, rotational motion is somehow not linear when it is, in fact, linear.
Use if we're trying to analyze the motion of this fulcrum system. So what can we use instead? Well, let's look at this system in terms of angular momentum. The total angular momentum.
So nothing really changes here. So I don't know if there's, is this really worth playing? Well, let's just get through it.
About an axis is conserved when there are no external torques acting, again, around that axis. So the axis that we're going to look at is this fulcrum point. Even if there is a force, an external force, acting at this fulcrum point, the torque due to that force, measured around that fulcrum point, is going to be 0.
So again, and that's just a weak technicality, frankly, because he's talking about when it's actually rotating. But in this case, we're not really rotating, so we are going to push a torque on either side of the bearing. But the whole point is that the bearing is supposed to be pretty efficient, so we're not going to lose much to it. It's like hitting a brick wall with a rubber ball. You're going to get back what you put in. The bearing's going to reflect. It's not going to absorb.
Imagine trying to open a door by pushing directly at the hinge. You can push as hard as you want at that hinge. It's not going to cause a torque to the...
So there's nothing here that's pushing directly into the hinge. So again, this analogy is totally inappropriate. Clearly, you're pushing with the rotation of the bearing, so you're not pushing into the hinge. You're obviously pushing on the door and opening the door. So I don't even know why he's saying that somehow this is the same or equates to pushing straight into the bearing. You're not pushing straight into the bearing. You're pushing perpendicular to the bearing.
Door, and it's not going to get that door to rotate. In the same way, if we're measuring our torques and our angular momentums around this fulcrum point, any external forces that are acting here will not cause an external torque. So we can use this conservation of angular momentum.
So again, it doesn't make any difference. He hasn't changed any of the rules of how this thing works by changing whether you're going to think of it linearly or think of it angularly. So of course he's drawing his arrows as straight lines, even though he's supposed to be drawing them as rotating lines. So this is all just semantic wordplay.
So let's see how we actually calculate this. For angular momentum, if I have a point particle moving around some axis, the angular momentum is...
It's exactly the same equation. This is the law of the lever right here. You're just saying the distance times the momentum, the velocity, and the mass. That's all. There's nothing else here. Hasn't changed anything.
Defined as the cross product between the vector that points from your axis to where that particle is located, crossed with the momentum of that particle. Now, for simplicity, we're going to just say I'm dealing with rotations just in a plane. We're not going to worry about the full vector version of angular momentum, other than to just...
And it wouldn't matter, because frankly, the energy of the object is not being absorbed, making the rotation, because it's attached, if you were actually spinning a flywheel, for example. So there's no real forces on the attached matter.
Just say we can have motions that are counterclockwise around the axis and motions that are clockwise around the axis.
And totally irrelevant.
So we can kind of simplify this to how far are you from...
I mean, this is how weird their science is, frankly, is that they're going to sit there and say that somehow it matters that you push down in this direction and this moves up in this direction. And they're going to argue that somehow this is negative motion and this is somehow positive motion, when clearly they're both positive motions. This is a positive movement here that causes a positive movement here. And that's all that's taking place. I mean, it really is that simple. It's a rope going over a pulley. There's no way that you can rationally say that the energy you pull down with is somehow different than the energy on the other side of the pulley.
The rotation axis at the closest point of approach times the mass of the object times its velocity. If I have an extended object, some larger object that's rotating, we can calculate its angular momentum around that same axis by measuring both its moment of inertia, so that's this value I.
So that's nothing, okay? That's just the mass in its position. So you're just basically saying because I've put it in a different position, it weighs a different weight. But that's it. There's no inertia. There's just mass.
Measure of how much mass is there and where is that mass distributed. If there is more mass further from the rotation axis, so if
I mean, duh. So again, the argument is kind of simple. He's just describing, again, a lever. A rotating disc is the same thing as a lever. There's no difference. You have something twice the distance, it has to move twice as much in the same amount of time as something on the inside. So obviously, in a sense, it's twice as heavy if it's on the outside, because you have to move it twice as much. It's not its inertia. There's no inertia, okay, that has changed. There's just the fact that you are, in fact, going to move it twice as fast. And if it weighs the same amount, then you're going to need twice as much energy to move that twice as fast.
rotating around some axis, if there's more mass further from that rotation axis, it's a larger moment of inertia.
So it's not a moment of inertia. The fact is, it just requires you to move the matter more distance in real space. It's going to move more real distance in real space.
And the angular velocity. So it's the moment of inertia of the object times the angular velocity. If we have this...
It is its velocity. It's not its angular velocity, it's just its velocity period. How far does it travel in how much time?
Extended object that is rotating. And for a uniform bar, well, that bar has some mass. Its mass is distributed around its axis.
So this bar part is, this is the error. This is the part we're just looking for how much do we lose to the system. So that's the factor that has to be in either, whether you're doing this linearly or you're doing this angularly, it doesn't matter. You still have to account for the mass of the lever, unfortunately.
And for a uniform bar rotating around its sensor, that moment of inertia is going to be 1/12 the mass of the bar times the full length of that bar squared. So we have a way of calculating. I'm going to make sure I get the masses of any levers.
So all of that, in my opinion, is arbitrary to just doing the experiment, seeing how much it actually does require. So that calculation, I say 1/12 of the square of the distance of the bar, when you have to know what the bar is made out of, and you have to know how much it weighs. But whatever.
That I'm using, I'm going to get their length so we can actually calculate what this moment of inertia is. So let's say we're looking at the system before mass 1 hits the lever. Well, in that case, the only thing that's moving is just mass 1. So we've got the angular momentum of that point particle around the axis.
So there's no angular momentum. It's a linear thing moving on a track, okay? It's going to be a car on a track moving in a straight line. So there's no angular momentum.
So that's going to be the distance r1 just before it hits the lever.
So that can just be the same distance that's in the law of the lever. You're just saying how far is it from the fulcrum.
Times the mass of that object times that initial velocity that it's traveling at before it hits the lever. So that's how much angular momentum we start with.
So it's just exactly the same mathematics. It's just nothing's changed. It's exactly the same as if you were dissecting it linearly.
Afterwards, well, mass 1 might be moving. For now, we're going to say...
So my whole argument would be is if you do the experiment correctly, that is, if you have the half mass at twice the distance, or twice the distance accounting for how much momentum you've lost moving the actual lever, that all of the energy from the mass 1 will be consumed and transferred to mass 2. That's the whole point of the lever, is that it can do the conversion.
If it's moving down, I'm going to continue to call that a positive velocity. If it bounces back up, I'm going to call that a negative velocity.
So I don't even want to talk about positive and negative crap, because it's just that crap. There's no such thing as a negative motion.
This lever is going to be rotating with some angular velocity, and this lever has also launched mass 2. So mass 2 is now going up, and this velocity 2, I'm also going to call this a positive velocity if this object is going up, because all of that is associated with a counterclockwise motion. If m1 is moving down, that's counterclockwise around this axis. If this lever is rotating counterclockwise, we've got that counterclockwise motion, and if this mass 2 is moving up on this...
I think they're both going the same counterclockwise, but regardless, it just doesn't matter. If this still has motion, this can't have it. If the bowling ball is still moving, then it didn't hit enough pins. I mean, come on, it's just the energy goes from one object into the other object. That's how reality works. Now, they think something different is happening, But I'm going to assert what Newton, Descartes, and Galileo understood was that energy is transferred from one object to another object. You can transfer it completely or you can transfer it partially, but it's a transfer. There's no movement without using something else's movement. Something that is moving has to move something or change something's movement. Nothing not moving can make something move.
Side of the rotation axis, that's again getting us our counterclockwise motion. So that's what I'm defining as my positive direction. So if we take these objects, well, m1 might have some angular momentum, and that's at distance r1 times m1.
So this is exactly the same as the law of the lever again. There's nothing's changed here, okay? It's just the distance times the mass times the velocity, and that's all there is. And then he's added the I bar thing, which is just the friction, the waste, the what you're going to have to apply to move the lever itself, what the lever is going to steal from the experiment.
1 times v1. Object 2, mass 2, is at a distance r2 times m2 times v2, and we've also got the moment of inertia the angular momentum of the bar. It's moment of inertia times that angular velocity.
All it's going to add up to is a percentage of the energy it's going to consume.
So, since there are no external torques acting on this system, we have conservation of angular momentum, which means I can put these two equations together and say that in total, for any of these collisions, I should have conservation of angular momentum, where r1 times m1 times that initial velocity before the hit is r1 times m1 times v1 plus r2 times m2 times v2 plus the moment of inertia of the bar times that angular velocity. Now, this is making some assumptions. We're assuming that the fulcrum itself has very low friction, so we're not getting any...
Again, I wouldn't do any of these assumings, so test that. And the test is merely to see how much energy does something lose when it hits just the lever, and that'll tell you a lot. Yeah, a lot.
External torques due to friction, but again, as long as there are no other external torques acting on our system, which we should be able to control for to a pretty high degree of accuracy, then this conservation of angular momentum equation should hold for all of these collisions. So this should be satisfied in all cases, but there is a problem with trying to use this angular momentum alone.
So again, he's just going to play this math game that somehow we're not going to be able to measure these values when of course we are going to be able to measure them. So there isn't any problem. Yes, predicting ahead of time is just a matter of your model. What does your model say is possible? If you're going to conserve the momentum, the answer will be discernible. If you're not going to conserve the momentum, then you don't know what the answers are. But frankly, if you know the velocity going in, the mass going in, there's just no choice about what's coming out.
We can say, I can pick my R1 and R2 values. I can pick the mass values, M1 and M2. I can pick...
Why would you do M2? What will be? Yeah, you can pick the mass values, but the one you have to know is the initial velocity.
How fast, or at least measure how fast is that original object being thrown. But we've got one equation with 1, 2, 3 unknowns. We don't know what the final velocity of...
So again, more nonsense. You can already predict it by just telling you what the initial velocity is. So if I tell you what the initial velocity is and you know what the masses are on the lever, and you know the distances, then you've already solved for V2. So again, this is a fake formula in the sense of this fake notion that somehow we can't solve when yes you can solve. You've only got one unknown, V2. Everything else is a known. That's your prediction. Your prediction is we already know what's going to go in. We know where everything's arranged. We know where everything's placed. And all we want to know is what's V2. So you've got one equation with one unknown. You don't have a problem. I mean, yes, the I bar, we have to just assume that's whatever, 10% of the energy.
Object 1 is we don't know the final velocity of object 2, and we don't know the angular velocity of that bar afterwards. So if I want to actually be able to make specific predictions for specific cases, we need a little bit more information in order to get this to work.
So that's just silly. There's no other information you're going to get. And so all he's going to do is apply another formula to this formula and pretend it's going to give him information when it can't give him any information. You already got all the information you can get. You can't get any more information without doing the experiment and measuring V2. So without doing the experiment and measuring V2, you're done right here. This is as far as the equation goes. One equation, one unknown.
We need to know something about what type of collision are we dealing with. The objects that are hitting, are they elastic objects that are going to bounce off and maybe do a better job at conserving kinetic energy? Or are we going to get an inelastic collision?
Well, you can't predict that with your equations either. So you have to know that from knowing what a Newton's cradle does. They're clearly elastic steel objects. They clearly will bounce off of each other. And clearly, in the case of a Newton's cradle, the energy just moves from one end to the other. It doesn't bounce in any way. There is no reflection. There's just a complete conversion of the energy in one object into the other object. And that's what I would claim the lever is proposed to do, is to merely create a circumstance where the a high acceleration can be converted into a slow acceleration. You can just convert, something going fast into something going slow, or vice versa.
Where the object kind of sticks to the lever afterwards. So, in order to get more specific than this, again, this conservation of angular momentum should be conserved, should be holding true in all of these cases. But we want to make sure.
So again, and if you just went with this formula, the prediction doesn't give any room, for any other answer than the 2-to-1 answer. So if we say the I bar was 0, that is, we lost almost nothing to the lever because it was ultra light and it's consumed very little, then the V2 for half the mass would have to be twice the velocity. And that would violate in the sense that would create free kinetic energy. So he can't let that happen. And so all the rest of this is just a way of trying to prevent that from happening. But that's in fact what would happen with this formula. That's what this formula says the answer is. If I cross out the I bar and say there's no losses, V2, if M1 is 1/2, V2 has to be 2.
We know what else also has to be holding true. So let's start with the inelastic case. So I'm going to say we're going to work with a case where M1 sticks to the lever, so that would be an inelastic collision, and M2 is launched with a velocity matching the tangential velocity of the bar with...
Right, and I'm saying it's going to stick whether you like it or not if you have it located in the right position. So if this deceleration matches this acceleration, that is half the mass, then there's no problem. Now in this case he's putting the same mass on both locations, which obviously means this has to leave with half the velocity. But this cannot possibly retain half the velocity. So that part is, in my opinion, a nonsense. If you're going to make something that's the same mass at twice the distance, it has to get all of the energy to go half as fast. If you have any energy left over, there's no way it's going half as fast. It's going much less. So that prediction of his, I think, is easy to state will not happen. You will not have a circumstance where you only use half the energy on one side and give the other object 100% of the energy. That's not going to happen.
Ideally, no flexing of
the momentum, sorry.
Bar. Are we going to actually be able to get no flexing of the bar? That's probably going to be a bit of an assumption, but we'll again talk about that as possible sources of error a little bit later. So if we have these assumptions, well, we've got some additional conditions. If M1 sticks to the bar, then that angular velocity should be related to the velocity that this object has after the collision and how far it is from the rotation axis. Because again, this object is sticking to the bar, its linear velocity and how far it is from the fulcrum point is going to be related to how quickly is that bar rotating. Same for V2. If the V2 is being launched with a velocity matching the tangential velocity of the bar, so again, V2 isn't elastic, it's not going through its own kind of bouncing motion, it's just being pushed by that bar initially, then that angular velocity should also equal V2 over R2. And notice we can also relate V1 and V2 directly together. So V2 is just going to be R2 over R1 times the velocity of object 1, again, after the collision.
So he's basically just saying what I've already stated, but yes, frankly, but these numbers, again, this 1/2 he puts over here for M2, and he has M2 weighing the same, is not going to be possible if you still have half the energy moving down on the lever. Can't happen that way.
So let's take these conditions and plug them into our conservation of angular momentum equation. So if I sub some of these in, I can replace V2 with R2 over R1 V1, and I can replace this angular velocity with V1 over R1. Okay, so that's all I've done here. And I'm not going to go through all.
So, yeah, so I don't know what's the point of this, right? So the equation is the same for the first object, and it's the second object he's turned into r squared over r. So somehow squaring the distance of how far it is from the external lever, which would be 2, which means 4, divided by 1, which, is still 4. So this is where he's going to get a wacky number.
All the algebra steps, there's going to be some algebra steps that I skip in here. If you want to see me make a video with just lots of algebra steps, I can do that, but at least this one, the algebra isn't too bad because I can just factor v1 out of all of these terms. I think I also multiply both sides by r1 just to get rid of this, some of these r1s in the denominators here. But we can basically rearrange and solve for v1 in terms of where is m1 hitting. What is
So I would argue that these equations are nothing like the original equation he said everything had to meet. So this equation is now he's perverted this simple equation where we had one unknown, v2, and now he's created all of this nonsense. All right, you can't see it very well, but it's there. You can see it well enough, I think. Well, whatever. It's right here. It's a mess. That's what it is.
Mass and the r distance for object 1, what is the mass and the distance for object 2, and what was the initial velocity before the collision. We can also have the moment of inertia of the bar added in here as well. So again, these equations, they look kind of long and a little bit ugly at the beginning, but we have all of the information where if I know how fast this thing was launched, I can predict how fast object 1 should be moving.
Right, and I could do that with this first equation. So I'm just saying momentum tells me what it has to be. I mean, there's nothing missing here. So again, there's absolutely no reason not to be able to solve this equation as it is. It's only v2 is the only thing you don't know. You know r1, you know m1, you know v1, you know r2, you know m2, and the only thing you don't know is v2. And of course, the factor that you're losing to the lever. So there's nothing. There's absolutely has fixed nothing with this nonsense. So converting this simple equation into this complex mush. How did that improve the equation?
After it hits and sticks to the bar, and how fast object 2 should be moving after it's launched by the bar. We can look at some particular cases. So again, these are just the two equations that we just derived. And for this one, let's just look at a couple of cases saying we're going to assume that the bar's moment of inertia is fairly small, like assuming a low mass bar. Well, we can make some predictions.
Okay,
if
so
M1
so he could have done that with the first original equation, right? Just got rid of the I bar part and got rid of the I bar part. And we'll just say that it's 100% efficient, which is very nice, but obviously it's not going to be the real world. So, it's not very useful to use an idealization when you're going to do an actual physical experiment that isn't going to have an idealization. So, it's sort of a cheat right there. But anyway, these predictions are, in my opinion, silly. But let's go. I'll just do it here. Right, so the first one, he has M1 equals M2. So he's got a heavy mass, a 2 mass, and a 2 mass, let's just say. So he's got a 2 mass, twice the distance in the fulcrum. Obviously, it's got to go half the speed. All right. But obviously, the only way it can go half the speed, that is, the only way it can get that much momentum, which is all the momentum the first object had, it has to use up all the energy from the first object, and he has the first object still moving at 1/2 the velocity. So somehow it only loses half its velocity, and it gives something that essentially weighs twice as much as it weighs half the velocity. You can't do that. That's way too much momentum.
two are the same and those distances are the same, and you plug that information into these equations, well, v1 will be half the initial velocity.
Right, so v1, like I'm just saying, all you're doing is saying, look, I'm going to change this acceleration rate. This object has to, the idea that it would stick is, it wouldn't, okay, because frankly the 2 mass at twice the distance essentially weighs as much as a 4 mass. So it's like banging a 2 mass into a 4 mass, which means you're going to get a reflection. It's not going to continue to travel through the object. It's going to bounce. That's what its tendency would be. And so you're going to force it to stick, all right? But it's not going to matter because it's not going to be able to get the energy into the other object because they're of the mass differentials. So if it sticks, yes, it's still going to lose all of its energy, and this is going to leave with 1/2. So yeah, my prediction is 0 here. V1 will be 0, and V2 will be 1/2.
That it was moving at. And V2 will also be half of the initial velocity that M1 had as it was coming in just before hitting the bar. If we say, well, let's do the case where M2 is half the mass, so M1 is equal to 2M2. So M2 is half the mass, but at double the distance. Well, if we have this inelastic case, object...
So that's the experiment we want. That's the one where they're going to make the free energy. And he comes up with this number of V1 still has 1/3 of its motion, which, why would it still have any motion? And he's saying R2 leaves with 2/3 the velocity. So it's not even that it leaves with 1 velocity. He's saying it's 2/3 the velocity. So it's a half mass object, and it's only going to leave with 2/3 the original thing's velocity. Now, that to me is silly. Frankly, there's no way that's going to happen. It's going to be 1 point something. I say it's going to be close to 1.8 because of the loss from to the lever. But outside the loss to the lever, it's going to be close to 2. It's going to be going twice as fast. So obviously our predictions are way different. But I don't think there's any chance you're going to get this V2 number of 2/3 of the initial velocity. It's ridiculously slow. It's going slower than the original heavy object went in. So the lighter object, he's saying, is going to have less velocity than the initial object had going in, which is, in my opinion, just ridiculous. No chance. All right, take a pause. All right, back. So anyway, so this 2/3 of the initial velocity, again, the lighter object twice as far out is essentially the same weight. It's not going to move at 2/3 the velocity because just ain't going to happen. Yeah. Let's see how else to say. I mean, it's a lighter object. It's half the mass. And it's at twice the distance. The law of the lever says it has to be something over 1 anyway. So it can't be 2/3. It's just a crazy number. But anyway, continuing.
Object 1 should be going at 1/3 of its initial velocity, and object 2 is going to be launched at 2.
So again, this whole idea that the energy won't be appropriately converted into the other object, and somehow you have leftover energy, that it won't be used, I think is just wrong-headed.
2/3 the initial velocity of object 1. Remember, the alternative model that was being proposed is saying, oh, V2 should be launched with twice the speed.
Yeah, with the sacrificing what the, like I said, if you're going to say it's an ideal lever, okay, and it doesn't consume any energy, then yes, your first equation would obligate that answer. So the equation before you turned it into this slop, that equation obligated the answer of 2, twice the velocity. So before you did all of this replacement math, totally unnecessary. Let's recognize totally unnecessary because he already has the R values, he has all the M values, and all he's missing is 1 velocity value. That's it. That's all that was missing from the equation. So he just pretended he had 3 unknowns, okay, in one equation when no, you only had 1 unknown. And the friction, of course. But you eliminated the friction in all of this formulation. He took all the friction out. So he's saying that this 2/3 is the answer before friction is going to steal some of it. No chance.
That mass 1 originally had before hitting the bar in this particular case. That's nowhere near what we're getting for this prediction, so we have different predictions for what should happen to this system. We should be able to gather data and look for which model is better at predicting the motions of this particular system.
Right, and it was really wrong of you to say that the I-bar isn't a problem. It's going to be a big problem with the experiment you're doing, because you're not going to have a nice 10-to-1 relationship between the mass of the carts and the mass of the lever. You're going to have some lesser relationship, which is going to be a problem.
If we say, oh, let's do the m2 is 1/3 the mass, but at 3 times the distance, well, we get different predictions for the velocities of objects.
It doesn't even make sense. 3/4 the velocity. So it's 1/3 the weight. It's 3 units of distance out. Somehow it's moving 3 times the distance in the same distance the other object moves. So a little tiny movement here is 3 times the movement out here. And he's saying 3/4 of the velocity. How could it possibly be 3/4 of the velocity? So just a nonsense statement. So again, he's not using velocity as velocity. He's not talking about distance. He's talking about how much angular rotation or some other kind of crap. But I don't even know how you could use angular rotation. It's still a small amount of degree changes here and a big degree change over here. So I don't even know how he gets away with that. I guess he's saying it's the same angular velocity when this one's moving twice the speed. He's saying it's the same angular velocity because it's going to rotate in the same number of times. So he's saying that this small distance is the same as this big distance. All right, so let me just draw that. So that's where he played the game. Okay, got it. That's what just ruins conversation with physicists. Is they just keep changing the goalpost, as they say. Velocity in this equation doesn't mean velocity. All right, it means how much distance you're turning in an arc. So again, if I drew it as a gear, you could really understand it. All right, so I just draw it as a gear. All right, that if I had 2 gears, you could understand that one gear, okay, so if I move the gear this much, 90 degrees, okay, so I'm going to move the gear 90 degrees. You can see that this distance, okay, is very small compared to this distance. It's a 2-to-1 relationship. This is twice the distance that this is in terms of how much distance is going to be moved by an object at these 2 locations. He's saying their angular velocity, that means how many rotations they're turning, is the same. Yes, this small distance is the same rotation distance. It's the same 90 degrees. But obviously, okay, it's not the same. So he's saying that this will be 2/3 of the rotational distance. So he's saying it's something like that, 2/3 of the rotational distance. So he's saying that this will be the amount of velocity for the half mass, okay, twice the distance. It'll be this 2/3. Well, 2/3 would be a little bit more over here. Okay, so he's saying it's the difference between this distance, this full arc, and this distance. So this is obviously 1 plus extra. So we're back to the 1.4-ish kind of number, probably, he's claiming. But yeah, he just screwed up velocity. We know we're going to be measuring linear velocity, right? So he's got an equation that gives him an answer, 2/3 the velocity, when he's not really measuring velocity, okay? It won't be he isn't measuring a real velocity because the carts are going to be moving real velocities. They're going to go real linear distances. That's how you're going to measure. So when the lever moves, it's going to move the cart in a straight line, okay? You're going to see these straight lines. This cart comes in, this cart leaves. This is the velocity you're going to be measuring, is a real velocity, okay? You're not measuring an arc velocity. So it's just bogus. It's not going to be, and these fractions are nonsense. There's no way the lighter object moves slower than the object that came in. No chance that's going to be the measured velocities. So I don't know what use this has, because this isn't going to be the velocity he's going to measure when he measures the cart's velocity.
Object 1 and object 2 afterwards. And again, these are cases that we are going to be testing. So again, right now, these are predictions, and we should withhold either accepting these predictions or rejecting them. We should withhold judgments in time.
No, I can already answer the question. Like I said, I saw the original formula. I already filled in all the blanks and I already got the right answer. So by the original formula, if I assume a perfect lever, ultra light, I already know what the right answer is. Your formula already gave me the right answer, which is half the mass, twice the speed.
Until we actually do the experiment. But one of the things in the alternative model that has been proposed, there was this requirement that it always has to be in this balanced state. If m2 is half the mass, it's got to be at twice the distance in order for...
Yes, outside of friction. So again, I can't explain it 400 times, 700 times. I made it clear in my initial video in a conversation with you. I said what you initially have to do is see how much the lever is stealing. How much energy is it stealing? Obviously, the other object can't move the lever and the other object. It can't give them both its energy. So if the lever's taking energy, you have to subtract that. Duh.
For DraftScience's model to be able to make predictions. At least I haven't heard any other kinds of predictions. But this model says you can set the masses to be...
So what did he just say? I mean, my model hasn't not answered the question. I mean, what the hell was that crap?
But one of the things in the alternative model that has been proposed, there was this requirement that it always has to be in this balanced state. If m2 is half the mass, it's got to be at twice the distance in order...
If you want to do the conversion, that's right. So if you want all the energy to go from one object to the other, you have to have big M, little v, big V, little m in exact proportions. If they're not exact proportions, then you have the Newton's cradle problem back again, where you won't be matching the acceleration. The acceleration of the lighter object won't be matching the deceleration of the heavy object. You have to match the accelerations. That's why there's a law of the lever.
For DraftScience's model to be able to make predictions. At least I haven't heard any.
So nonsense. I can make predictions if you put it in closer and you put it in further away. Obviously, if you put it further away, it's heavier. So that's like a light thing banging into a heavier thing. If you move it in lighter, then it's still lighter, but it's so light that now it can't take the energy because the velocity isn't high enough. Because you've not put it on the higher arc, therefore it's not going to get the high enough velocity, so therefore it can't take all the energy because it can't get enough velocity. Just like the first bowling pin can't go 500 miles an hour away from the bowling ball. It can't take all the energy. It can only take the energy the ball can give it, and the ball can only give it the energy it has, the velocity it has.
Other kinds of predictions. But this model says you can set the masses to be any values, and you can set them at any locations.
So there was nothing in my model that can't do exactly the same thing. So just a bullshit. Why would I predict an experiment I don't intend to do? Why would I do, well, let's test a mass that is 63 grams with a mass that is 78 grams? Why would I do that experiment? Shit. It's 2 to 1 just to make everything easy, or 4 to 1, or 3 to 1, to make things easy. Obvious. Why do the unobvious?
So if I just did m2 is half the mass, but they're both at the same distance from the fulcrum, so it's evenly spaced around the fulcrum, we can predict how fast are those going to move. They should both be...
Yeah, I can predict it too. So, but again, the real experiment to do is the one that shows momentum works and kinetic energy fails. So that's the one I like to do.
Moving at 2/3 the initial velocity. If I said the masses are the same, but object 2 is at twice the distance, well, we should get 1/5 and 2/5 of the initial velocities for objects 1 and 2 respectively. We can again...
So these aren't real velocities again. So again, this is absolutely useless chatter, because these aren't real velocity numbers. The velocity is going to be measured based on how fast the cart is moving, not how much arc the lever's moving. Okay, you're not going to measure the arc of the lever's motion. You're going to be measuring the velocity of a linear cart. So again, this is just so bogus.
Make specific predictions, and these are more cases that we're going to be testing. To make this a little bit easier to work with, I've actually put together, and this is going to be something that we use in the when I actually do the data analysis. I've put together a quick little Excel document that actually goes through these calculations. So if I have
I mean, this will really screw the pooch here. Okay, if he's gonna sit there and mess with this, let the computer tell you what the right answers are, crap. Okay, then I'm gonna call foul right there. I mean, this isn't complicated. Measure the mass, measure the velocity. That's all you need. Mass and velocity. You don't need anything else. Don't need a computer to do anything for you. So this, yeah, bullshit.
Everything, same masses and same distances, then what these ones are calculating is what happens in this inelastic case. Notice this equation here, hopefully you can kind of see it decently on this on the video. We've got the R1 squared, so that's cell B3 here, squared, times B1 for mass 1, divided by B3 squared, so R1 squared times mass 1, plus R2 squared, that's this cell, times M2. And it also takes into account...
Yeah, whatever. All of that's not going to get a right answer. So that 2/3 stuff ain't going to happen. None of that crap's going to happen. So no chance. The lighter object is not going slower than the initial velocity. No chance.
The effect of the bar. So we're actually going to be able to incorporate into this model what about the fact that the bar is not necessarily a completely negligible mass. So if I add in the moment of inertia of the bar, we can see how those predictions are actually going to be updated. Again, I don't think the alternative model has any mechanism, that at least I've heard, of being able to make these kinds of predictions.
Oh, what a fucking bullshit. Again, why would I do it? It's momentum. It's mass times velocity. Big M, little v, convert into big V, little m. Okay, I don't need a computer to do that. Ugh, amazing, fucktarded bullshit. Multiplying by the distance is all you're doing. You're just saying, what's the difference in the distance? The difference in the distance will tell you whether or not you can do the conversion. But again, it's going to change the experiment fundamentally in the same, it's just like in a Newton's cradle. If I change the mass so the two objects don't have the same mass, then I'm guaranteed to get a reflection. Or I'm going to have two objects going that way. Okay, the energy won't be converted into the other object. So the only point I have emphasized is if you want the complete conversion, and that's what we're after here, is to take all of the energy from the 10-ton train going 5 miles an hour, and we're trying to convert it into a 5-ton train going, yeah, that's the objective.
Being able to improve on these kinds of predictions. So I'll set that back to 0. So again, just kind of comparing with some of these other cases, we said if M2 is half the mass, but at twice the distance, then the initial velocity should be 1/3 of, the velocity of object 1 should be 1/3 the initial velocity.
Right. So again, if the conversion is successful, there should be no leftover motion in V1, okay? M1. M1 should have no velocity, just as in a Newton's cradle. The first object, V1, should go to 0, and V2 should be the initial velocity. We're doing the case where we're going to do something with half the mass, and we're going to hope to get all of the energy from V1, object 1, into object 2.
The velocity of object 2 should be 2/3 the initial velocity. Again, these are just saying initial velocity is 1, it's just a factor comparison. If I go to 1/3 the mass at 3 times the distance, well, there's our 1/4 and 3/4 values. And if I do half the mass at the same distance, so half the mass at the same distance, again, we can make these predictions. This is the 2/3 value, they're both at 2/3, and if it's the same masses at twice the distance, that gives us our 1/5 value and our 2/5 value.
So there's just no chance. Again, lighter objects will go faster than the initial velocity. It's just a ridiculous argument to say the half as light object is going to absorb less velocity than the object hitting it. It's like a bowling ball hitting a bowling pin, and the bowling pin goes less fast than the ball. Yeah, how could that happen? Oh, that's right, it can't happen.
So again, these are things that we're going to be actually doing when we actually get the data for the experiment and be able to incorporate in what is the effect of the bar as well. But this has all been in the case where the object 1 stuck to the bar. That's not the only case that can happen. There are other cases. So let's say I've got a new case where M1 is an elastic object. When it hits the bar, it can bounce off of that object. It's like a rubber ball. And M2...
So this is where he really gets, in my opinion, silly, because none of those reflections go through the fulcrum. The fulcrum stops any bending from going to both sides. It's really not going to happen. So this would only apply if there was no fulcrum.
We're going to say for M2, we're going to do the same thing as last time and say M2, it doesn't deform. It's not like I've got another elastic ball on the other side. It's just going to be pushed by the bar, and we're assuming, again, no flex for the bar. Again, these assumptions are things...
This very idea that he thinks twice the energy is going to go into the bar is... I just don't know why anybody takes that seriously. He's going to make free momentum here. Okay? He's going to say he can put 100 momentums into the lever and he can get more than 100 out the other side. I mean, it's bad enough when they think they can make free kinetic energy, but when you think you can make free momentum, it's just too silly.
That are not going to be exactly matched, but we should be able to get pretty close to having these kinds of conditions. A couple of things to note. If M1 ends up bouncing backwards, then this velocity would end up being negative. We're still saying for M1, down is the positive direction that we're going to call for velocity because it makes that counterclockwise motion, and up is the positive direction for velocity 2. So if M1 bounces back, that just means V1 is going to be negative.
So again, I just don't know how anybody with a brain that works can sit there and play this game and think there's any such thing as negative motion. All motion has to come from something. Something has to give it motion. 100 in cannot make 500 that way and 500 that way and 700 this way and 700 that way because they cancel or some other kind of bullshit. Can't happen. All it can do is make 100. You can't put 100 in and get 100 plus out. Can't happen.
Since we're launching this mass the same way, we can still say that angular velocity is related to the velocity of object 2 and that R2 distance. And we can again apply this to our conservation of angular momentum equation. So if I say that this angular velocity is V2 over R2, I can replace that angular velocity in this equation. And to simplify the algebra a little bit, I'm going to combine some terms, because notice we've got a V2 on both of these terms. I'm going to factor that...
So again, we know all of this information again. So we have all the answers except for the realistic number for the bar. He doesn't have that. Okay, so we don't know how much momentum the motion of the bar is going to consume. All right, but we have all the rest. Why are we going to change anything? Why does the formula need to be changed? He's not going to fix this part. He's just going to mess this part up again. Why? We already have all the variables except for one. We just want to know V2. That's the only thing that's missing. So this is just such a cheat.
Do a little bit of rearrangement and say that my conservation of angular momentum equation becomes R1 M1 V0 equals R1 M1 V1 plus R2 times this value of A. This is the mass of object 2 times the moment of inertia of the bar divided by R squared, and then times V2. This method of saying I've got this combination of terms, and I'm just going to switch that for a new parameter, this can be a very, very useful method of simplifying the algebra. I'll probably do another video on just this method of trying to simplify algebra by having, you can kind of think of this as the effective mass of the object, of object 2, saying I'm also taking into account the effect that the bar has on...
So how this all should always be tested, and they never do, is just test the formula before, okay? So do the experiment where you have all the variables now. You don't have to calculate it. You know V1, you know V2, you know M2, you know every one of these variables. Do the equation and see if your new equation gets the same answer as your old equation. Because if they don't, then all of this is just shenanigans.
How object 2 is going to move. But with that in play, what other equations? Because we still have two unknowns in here. Well, if M1 is colliding elastically and we don't have any deformation in M2, we should be pretty close to having conservation of the kinetic energy of the system. Again, there's still probably going to be some vibration in the bar itself.
So the nonsense of conserving kinetic energy by creating free momentum. So we'll make free momentum so they can conserve kinetic energy. So as I pointed out, he did an experiment, same spring compression. He made the same spring compression, right? Puts light objects in front of the spring, 200 momentum. Puts twice as heavy objects in front of the spring, 400 momentum. Where does that go but ludicrous? So the lighter objects I put, I get less and less explosion out of the explosion. And the heavier the objects I put in way of the explosion, somehow the explosion makes more momentum. It's just nonsense, frankly.
But hopefully we'll get pretty close to having an elastic collision. So if that's the case, we can take our equation for conservation of energy. Before the collision, we just have the kinetic energy of object 1, with that velocity before the collision. Afterwards, mass 1 is going to be moving, it's got some kinetic energy. Mass 2 is going to be moving, it's got some kinetic energy. And the bar is also going to be rotating.
So the ideal would be is for him to put this way out on the lever. So do a 4-to-1, do a 6-to-1. Because then he'll guarantee that he puts twice as much energy into the lever, right? So he's doing the bounce equation. So the bounce equation means that you throw the tennis ball at the brick wall. The tennis ball theoretically comes back with 100%, but it obviously doesn't because tennis balls aren't perfect, aren't efficient. So let's just say a Super Bowl, something closer to 99 or 95%. You get your energy back, plus you put 2 momentums into here. So if we went in with 100, you get 200 in the brick wall by magic. It's 200 momentum. Now, even though the brick wall isn't moving and has 0 velocity, they say it's calculated to be 2 momentum. Even though it makes no sense, that it's obviously not there, because they claim it made the whole Earth move. Okay. When no, all it did was reflect. If I throw the rubber ball and the brick wall moves, the ball bounces back with less energy. The more the brick wall yields, the less I get back. That's how it really works.
Though the center of mass of that bar is still fixed in place, all those moving parts mean that this object has kinetic energy. This is the equation for the rotational kinetic energy of a purely rotating object, an object that is just rotating around some axis. Well, one thing that we can do with this is actually simplify it again using this exact same factor that we had in the previous equation for looking at conservation of momentum. And say that, well, if I have this m2 times the moment of inertia of the bar divided by r2, we can combine these particular points. Again, I'm also using that this angular velocity is the velocity of object 2 divided by r2, and that's where this r2 squared is coming in. Again, I do encourage people to try to go through the algebra for this on your own. If you want me to go through the entire algebra and do a video on that, let me know in the comments. I just thought...
No, what I want you to do is take the original equation and then take your bastardization and then get the final answers after you do the experiment and show how you got the same answer with both equations, which you won't do because you won't get the same answer.
We try to keep it. It's already going to be a long video, so let's keep going with this one. So we have this equation for the conservation of kinetic energy, and we also have an equation for the conservation of angular momentum, again, around that axis. And now we have 2 equations with 2 unknowns. So we can solve this algebraically. It does take a fair bit of algebra. Again, if you want to see the algebra, let me know in the comments, and I'll do another video kind of going through these steps. But basically, we can derive 2 new equations for what's going to be the velocities of objects 1 and 2 after the collision in terms of the 2 masses, m1 and m2, the 2 r distances, r1 and r2, and the moment of inertia. This capital A term includes that moment of inertia of the bar.
Right. So again, he's predicted the moment of inertia of the bar, which he doesn't have. Okay. So he doesn't have any of those variables. So I don't even know what the point of that calculation is in that sense, because frankly, it's already that's the biggest unknown. How much energy is the bar stealing is really important. Yeah, really important.
So once again, we have a tool that we can then use to predict how the objects 1 and 2 are going to be moving after this collision. How is it going to be launched? So let's again look at a couple of cases for this. So again, here's our summary equations for this elastic case where M1 is acting like a bouncy ball and hits it, and M2 is just being pushed forwards and there's no flex in the bar. So again, a couple of assumptions there. We'll see when we do the...
If the ball bounces back, then it won't move this at all, okay? So if you bounce the ball back with 100% of the velocity that went in, you'll get nothing from the other side. No movement.
Experiment how accurate those assumptions were. But again, for this calculation, let's say that the moment of inertia of the bar is small, so we have a relatively low mass.
So he's playing the same game again. All right, so we're going to, after, even though you did this whole I-bar thing in the calculations, you're just going to pretend there's no I-bar. Okay, whatever. That isn't going to be true in your experiment. It's not going to be true.
Mass bar compared to some of the other masses that we're using. If we have the case where the masses are the same and those R distances are the same, then object 1 should completely come to a stop. Like, the bar is still going to be moving, but M1 hits and completely goes to a stop and just launches the bar, and that other bar launches object 2 at exactly the velocity that object 1 had beforehand. And you can kind of trivially see that if the bar has no mass, and we had a certain amount of kinetic energy coming in, because it had a certain velocity, the masses are the same, the velocity after didn't change, we still have conservation of energy in this particular case.
So he's saying M1 equals M2. M2 is twice the distance. He's saying it's going to leave with the same velocity that the first mass went in with. And it's going to bounce. I don't know. He doesn't give us that answer here. There's no answer here. So V1 will be 0 and V2 will be V0. So he's saying the lighter ball will go the same velocity as the heavy, their same mass in this case. So the same mass. So something that weighs the same but is twice the distance on the lever, he says it's going to leave with the same velocity the first thing had, which means it has twice the momentum. Twice the momentum. So he's going to throw a bouncing ball into the lever. It's not going to bounce. You know, by some magic. Okay, so some magic is going to make it not bounce. And it's... I mean, this wouldn't even work in a Newton's cradle. But anyway, and then it's going to give this twice the energy. So he's basically saying if I took a super ball in a Newton's cradle with a steel ball, and they have the same mass, that I can bounce the rubber ball into the steel ball and make the Newton's cradle ball move with twice the velocity? No, it can't. Not going to happen.
For the other ones, you'd have to go through a bit more calculation to confirm this. Again, I encourage you to try that. So if we have M2 is half the mass, but it's at twice the distance, well, then object 1 should actually...
So this will be the 2/3. Well, it doesn't say 2/3. It says 4/3. Yes, so it's going to have 4/3. So again, we already made twice as much momentum in the first example. So what's the difference, right? He's not showing the momentum numbers here, but yes, he just made twice the momentum in the first example. He doubled the momentum. So the momentum coming in is twice as much momentum coming out. Somebody thinks that's realistic, that I can actually do that. I can bang a rubber ball into a lever with a certain momentum, 100, and I can get 200 momentums out. Okay, so he's made a public video saying this. This is what they've done to physics. He thinks that's a realistic statement, that he's going to get the same velocity out. Now, see again, does he mean real velocity or does he mean angular velocity? So yeah, we're stuck again, right? Because now he's basically saying the ball won't bounce and I'll get just the same velocity out. See, that's the trick here. Is he talking about is V2 a real velocity? Again, he's going to do this experiment with motherfucking carts. Okay, straight line carts are going to hit the lever. All right, he's not using round balls or any of this crap. All right, so he's going to be measuring the velocity of the cart in a straight line. He's not measuring some sort of radian arc change. So this number is explicitly wrong. Okay, these velocities will not equal each other as linear velocities. I mean, it's just this is such a pile of crap. To use this same terminology, to say v when you don't really mean the actual velocity, you mean the angular velocity. You don't even mean angular velocity, you mean the angular rotational radians. It's just such bullshit.
Actually bounce backwards a little bit at a third of its initial velocity, and object 2 will reach 4/3 of the initial velocity of object 1. So again, even though this elastic case launches this with a higher speed, it's still nowhere close to that double the original velocity of the object.
So again, I'm fine. So as long as he's saying double, okay, in terms of linear velocity, then again he's still stuck with this. So if he's going to say double the velocity, then he's implying real linear velocity. So again, in this case, he's basically saying that yes, it leaves with twice the momentum. He's actually saying it will leave with twice the momentum that it went in with. That's what this equation right here says. That's twice the momentum. V2 leaves with the same velocity, okay, as V1, and it's half the mass. No, it's got the same mass, he says here. It's twice the distance, and he says it's going to leave at the same velocity when it's twice the distance. I mean, just to make any sense. All right, so V1, so it'll conserve 100% of the momentum. It'll just come out the same way, even though it's at completely the wrong places. There's no way it's going to happen anyway. It's a rubber ball. There's no reason for the rubber ball not to bounce off. So he's not going to be doing this experiment anyway. So there's just no point in even talking about it.
Again, we can look at other cases. If M2 is a third the mass, but at 3 times the distance, well, the launch velocity of...
All right, so all we need is this 4/3. So right there we got him. Okay, so let's just use this one. This is the one where it's half the mass at twice the distance. And he's basically saying that he's going to keep 1/3. The ball will bounce back with 1/3, and I'll get 4/3 of the velocity leaving here, which is more velocity than the initial ball had. But it's half the mass, so of course it's 4/3. It's going to be more than 4/3. All right, this just, never mind. He should just show what he means by momentum, and then this would be so much simpler. What percentage of the momentum is going to be in the object? But all right, so this is half the mass. And so V1 will be 1/3. So that's the Lewin thing. 1/3 reflection. Negative 1/3. And we'll have 4/3 going forward in the half mass. I don't even know how to make any sense out of that. Well, obviously, 5/3 is not, conserving the momentum. So you have half the mass at 5/3 the total velocities. So if you add both of the velocities, you have only 4. You're short of twice the velocity. But that's only because of the friction. So, well, anyway, we'll see what the real numbers are.
Object 2 should be 3/2 the initial launch velocity.
I think he's already done his experiments. So, I mean, I think, that's part of why he's putting this video up. But anyway, we'll see.
The initial velocity of object 1. And we can again do this in cases where it's not the balanced fulcrum case. So if M2 is twice the mass, if M2 is half the mass, but both objects are at the same distance, we can again predict how fast these objects should be moving after the collision. And again, we can use this same feature. Again, I did this for the elastic case as well. So if I move this down here, this elastic case, it's actually measuring r1 squared times m1 minus r2 squared times m2.
So again, this would be, look, when the half mass is twice as far out in the lever, it weighs the same as the single mass. So this is essentially a rubber ball hitting another ball of the same mass. And you're going to understand that, of course, part of its energy is going to go into the one ball and part of it's going to go to reflecting it. All right. So that's not going to be a news flash. I don't know exactly how he's going to do these elastic collisions. Yeah, with cars.
Times A. So I did this calculation of what A is equal to, the m2 times the moment of inertia of the bar divided by r2 squared. Basically, we are able to kind of go through this and calculate both the velocity of object 1 and the velocity of object 2. So again, just to kind of verify that this is working, if we set everything equal to begin with, then object 1 stops, object 2 just gets launched at the initial velocity of object 1. If I have m2 is half the mass at double the distance, well, there's our negative 1/3 and our positive 4/3. If it is m2 is a third the mass at 3 times the distance.
So way short, let's just understand, way short of twice the velocity. So he's just basically saying levers don't work. But again, why is he even injecting this stupid bouncing crap into this experiment? But anyway, whatever. We'll see.
Well, there's our negative 1/2 and our positive 3/2. And then again, we can look at this in other cases where m2 is half the mass, but it's at the same distance. There's our 1/3 and 4/3. Again, we can go through these different cases and identify these different properties. Again, these are all predictions, but these are predictions that we can then go out and test. So that's what we're going to be doing in one of the next videos. I do want to apologize that it's been a little bit of a delay in actually doing the lever experiment itself. It's been a combination of getting a bit of equipment and also just, life things taking place. And I did want to make these videos on which methods are going to be the best tools for the job in physics in general, for different kinds of questions, and going through these details on how the textbook model of physics would actually make different predictions about how this lever experiment should go. So those are the predictions, and again, I should be able to get the lever experiment done and recorded and posted next week. It's the week between classes for me, between terms for me, so I should have a little bit more time to work on that. But we'll call that good for today. As always, if you have questions about any of this, you can put those into the comments.
Whatever. All right, so again, we should just go back to the original formula. Okay. It's going to show it. Maybe not. We want 16 or so. 14. Somewhere in there.
Two are the same, and those distances are the...
So that's all you need. Right here's his formula. Oh, that wasn't the formula. That was after he made a mess out of the formula. Right, so here's the simple formula. Okay, and he has all of this information. Let's just understand, he has R's, he has the M's, and he has the initial velocity. So he could solve the equation just in this form without doing any of the other crap. Without doing all these derivatives and nonsense. So all of this is completely not useful because the formula is here. This is what your textbook says the answer should be. You've stated it, and by that equation, if I ignore I bar, the velocity at half the mass has to be twice the velocity. That's what your own equation says before you did this to it. All right, so I'm just making that clear, that this equation is solvable, and you chose not to solve it. And instead break it. Period. Nothing else happened here. You took a formula that gives my answer, momentum's answer, where momentum says this will be the answer. Okay, momentum says this is the answer. V2 is 2. Twice the velocity of V1. The end. That's the right answer. If we have no friction. If we have no problem moving the bar, if it's relatively light compared to all the other moving objects in the experiment, then V2 is twice the initial velocity. All right. If we put half the mass at twice the radius. Okay, so I just want to make that clear. that this isn't about a textbook. This is about the fact that they take an equation they say is the rule and they manipulate the equation to suit their agenda. Okay. And not to enhance the equation, not to solve the equation, but to solve it in the manner that they wish to solve it in, to produce the answer they want rather than the answer the facts say they should be getting. All right. So we'll see. Let's see if there's anything here. Comments will be crap. Thank you, Michael. Very clearly laid out and explained. Yeah, I don't think so. Showing how the tool of mathematics, whatever. Blah, blah, blah. This is one of those rare cases where I don't know what this even is, the psychological data of the reactions will be just as precisely predictable as the physics data from the experiment itself. Well, that makes absolutely no sense. Ugh, brother, Dick Woody. So this is probably all Farley. Even if you think it's a perfect experiment, you can count on Daft to find something wrong with it. Something you would have never even considered. So when Steve Gosling did the experiment from 5 times the height, dropping the weight, and claimed it was a proof, nobody should have spoken up and said, "You can't do that, Steve." I mean, you people are just so disgusting. I mean, you're just such pieces of goddamn scum. All right. So, thank you, clearly explained. Thank you so much. Oh, cool. Thanks, Dr. Michael. Oh, that's from Biro. He typed a little tripey comment. Cool. Thanks, Dr. Michael. Oh, he really is turning into a 4-year-old. Let's see. To be helpful and courteous to others. Oh dear, Michael, there's no use wasting good manners on that whatever orgy. I mean, it's not like it has feelings. That's Dick Wood again. All these comments from little Dick Wood. Ugh, God. He's talking about his eyes, Bucky eyes. Anyway, just too ridiculous. These comments are just so poor. Alright, so anyway, we'll see what happens. So I'll just reiterate, as I had repeatedly pointed out, the first step is to see how much energy the lever steals from the experiment. Do the 2 mass against the 2 mass at the same radius and see how close it is to getting 100% conservation of the energy. Alright. So till the next time and such. Oof. Yeah, I think we've been over enough. Yeah. So till the next time and such and so forth and whatnot.